All right. Yeah, this is awesome. This is like really a full house. Very exciting. So at work, I often have to apologize for having inflicted OCaml on James Street many years ago. And here again, I need to apologize for inflicting OCaml on you all. So this talk is going to be about, in some sense, it's about some particular technical problems that we worked through as part of onboarding the new Multicore garbage collector for OCaml. And in part, it's a story about technology transfer, of how ideas move from academic sources sometimes into industrial use, and what are some of the things along the way that you need to do to make that happen successfully. So like a little bit about OCaml, which Jane Street is a huge user of and has been for a long time. OCaml is an old language. It's like 30 years old, roughly, about as old as Java. And for a very long time, it did not have any kind of shared memory parallelism. And this changed in recent years. And like in some sense, this, Jane Street has kind of built its whole ecosystem around the kind of set of assumptions and properties that the language had. And now we're in a world where we have this new capability of being able to write shared memory parallel programs in the language. And this talk is kind of focusing on one aspect of that. But in terms of where to start about this, I want to start with a paper, which isn't really the beginning of the story, but it's the kind of important part of the process. So back in 2020, there was this very nice paper that landed in ICFP, retrofitting parallelism onto OCaml, that laid out the kind of design process and basic structure of the kind of design of the multicore garbage collector, and the ideas behind how it was built. The goal was to build a modern, high-performance multi-core garbage collector for OCaml that would be, importantly, easy to maintain and easy for people to adopt, right? They didn't want to make the process of maintaining OCaml much more complicated. And one of the design decisions that came out of that was one runtime. Lots of systems end up having multiple runtimes for different use cases. They wanted to have a single runtime that would be reasonably well optimized for both high-performance single-core workloads and high-performance multi-core workloads. So that meant to make it easy to adopt, it has to preserve the performance characteristics that you already had coming in. So sequential performance couldn't be changed. They couldn't really massively change pause times, right? An important part of a garbage collector is not just the net performance of your program all in, but what it does to kind of the responsiveness of it, how long you end up checking out, waiting for the garbage collector to do things. OCaml has a pretty good story in terms of having relatively small pause times. They wanted to preserve that. And they also wanted to preserve the FFI, the foreign function interface, because it's just kind of torture to go through all the C extensions that have been written and adapt them to a new set of invariants. I mean, the C extensions are already broken and have problems. You don't want to make it worse by having to change them all. And part of what the paper did is produced lots of benchmarks and evaluations to justify the design. So one thing they looked at a bunch of experiments and showed that the kind of loss of sequential runtime performance for the new GC was like on the order of like 3%-ish, which, seemed pretty good. Although every time someone tells you like the performance of a garbage collector, an important thing to remember is that a garbage collector's performance is not a point, it's a curve, right? A garbage collector is a thing that you can tune to have different behaviors, different trade-offs of basically how much work you do collecting versus how much memory you use. But in fact, the memory used was also shown to be relatively similar, and the pause times were also very similar. So that sounds pretty good. Like 2020, this paper lands as a new garbage collector, and also had good speedups, so that was nice. It did take a really long time, though, to get to that paper and to get after that paper to getting it upstreamed. So this is like 9 years of work from when the original multi-core project was born to when it actually got upstreamed. There are like, the green things are papers that were published there. There's a bunch of important points in time, like, in 2020, after the paper was published, the core team committed to working really hard to getting that implementation actually upstreamed. And like the ordering of that is like a real thing. I think if you want to convince the OCaml upstream community to accept something, you should probably write a paper or two to get them to accept it. But it's great, finally in 2022, there's this garbage collector that's easy to adopt. It's been upstreamed. Surely Jane Street, as a big user of OCaml, can immediately turn around and use it. No. So there's an extra like 2.5 years from what happened in 2022 to being able to use it us to be able to use it internally. Some of that time was not surprising. So the things marked in blue are just features that got added to the old sequential garbage collector while the new multi-core garbage collector was being worked on. And it was just kind of known that there was extra work to forward port these extra features. And like, they're good features. Prefetching is actually, I don't know, prefetching is kind of an amazingly good feature for a garbage collector. I was actually just talking to someone who worked on the Python garbage collector, which apparently copied some ideas from that design. It's like a great thing to add. So anyway, we had to like bring back all those features. That took a lot of work. But like the two orange points in the timeline are interesting. So like, I guess like the November 2023 thing was like, oh, we need to migrate to a new runtime. And like each version of OCaml has just one runtime. That's bad because it means to adopt the new language, you also have to immediately adopt the new runtime. And switching to a runtime is hard. So we're like, okay, let's just backport it. So we'll have like the latest version of the language supporting both runtimes. And then once we had that, now we can start doing experiments. And as soon as we started doing experiments, we're like, oh, the performance of this thing is like totally actually not acceptable. And then there was like a year and a half of working really hard on trying to understand what those performance degradations are and fix them. And that's what this talk is about. Okay, so I'm going to walk through, I'm going to kind of describe the garbage collectors to you. I'm not going to assume that everyone is like a garbage collection expert, so I'll talk a little bit of background about how garbage collectors work. And then we'll talk about some of the issues and what we learned about them. So first, what is runtime 4 like? What's the classic OCaml garbage collector like? First of all, it's sequential, right? Premise of the talk, it's not a multi-core collector. It's also generational. So a generational collector is built on what's called the generational hypothesis, which is a surprisingly stable and sort of broad observation about the behavior of programs in most programming languages, which is that memory dies young. The vast majority of things that are allocated end up not having very long lifetimes. And so as a result, you break up your collector into two different, you can take advantage of this by having really two garbage collectors that connect to each other. A major heap, where the garbage collector uses what's called a mark and sweep collector, and then a minor heap, which has a kind of brutally simple allocator, where it's just like, you just have a region of memory, and you just like, when you want to allocate, you just like bump the pointer forward, and then you do it again, and you do it again, and it's like 3 machine instructions to allocate a thing. And then when you get to the end of the region, you're like, okay, I'm out of space, what do I do now? So then you like scan the minor heap to see what's still alive. And if the generational hypothesis indeed holds, most of the things will be dead. You don't have to do any work to collect the dead things. And the live things you promote. You move them into the major heap, and they'll get collected there. And then there's one other clever trick you need, which is you need a write barrier. It's not the only way of doing it. There's like other tricks, but the trick that OCaml uses is a write barrier, which is basically a way of detecting whether there are pointers back from the major heap to the minor heap. So like, why does any of this matter? Like I said this thing of like, oh, we're going to scan the minor heap to see what's live. But you might wonder like, how can I cheaply scan just the minor heap? It's like this very small region and this other big major heap that has lots of other stuff. Maybe something in the minor heap is alive because there are pointers through the major heap to the minor heap. But if you imagine that you're in a completely functional environment where you're just allocating new stuff, like all the new stuff is on the minor heap and things on the major heap can't point to the minor heap, because if you're not mutating things, you can't create those pointers. So, and in a functional language, that's close to true. You have lots of allocations and fewer mutations. But when you do a mutation, you basically need to check whether you've introduced a back pointer and then do some extra bookkeeping. And that's the write barrier. It's the extra piece of code on every mutation that checks whether you've introduced a back pointer. So that's another part of the design. And then there's a mark and sweep collector. And so what is a mark and sweep collector? So the marker basically is going to start from the roots. The roots are the things that you know are alive, like values on the stack or values that you have in registers. And then you're going to go through and like mark everything that's reachable. You're kind of going to walk the object graph to discover what you know for sure could still be accessed. And then everything else you know can be removed. And then you have a sweep phase where you can walk over the heap and collect all of the unreached objects. And let's just like illustrate this for a second. So here is a little animation that I vibe coded with Claude Code, super fun, So here, like on this, you have the stack there, which indicates where in the roots, we just assume all the roots are on the stack. And then you have this object graph. Everything starts out red, unmarked. And then in the marked phase, you start walking through and just like turning everything everything green, right? You're going to go through and mark all the things. And now all the things that are red are the things that you know are unreachable because you couldn't get there. So those are safe to be collected. And then you go to the sweep phase. And the sweep phase doesn't walk the object graphs, it walks all of memory. So you just kind of go cell by cell. And then when you get to something that's marked, you're like, well, okay, that's marked, so it's going to stay around. And next round, I'm going to need to scan it again. So let's change its color to unmarked. And then you keep on walking. And every time you see something that's already unmarked, you're like, well, that's garbage, so I'm going to free it. And you just kind of keep on walking through. And the idea is, as you go and do this, you get to clear out all the things that you don't need. And in some sense, if you think about where that point is in the middle, the colors mean a different thing to the left of the sweep than they do to the right of the sweep. Right? So it's all about like walking through these garbage collection colors. So that's just to give you a rough sense of how a kind of classic mark and sweep garbage collector works. Differently from that picture that I just gave you, it's also incremental, right? So what does that mean? It means when you don't like just run the whole mark and sweep thing and have your program check out for all that period. You can actually instruct it to run for a period to collect a certain number of bytes in these what are called slices. You get these little slices that collect a few bytes at a time. And the idea there is that this makes your program more suitable for kind of soft real-time applications. You can build more responsive. There's some trade-off in terms of net performance. It's a little less efficient to do it incrementally for kind of bulk throughput, but you have much more responsive programs. And it's just like really important. Like you kind of can't have a reasonable programming language with like multi-gigabyte heaps with a non-incremental garbage collector. It's just kind of madness, right? All right, that's runtime 4. Oh, right. Oh, I shouldn't forget this. There's also what's called the snapshot at the beginning invariant. What does that mean? Once you're incremental, what it means is sometimes your garbage collector is running, and then sometimes your user program is running. Very charmingly, garbage collection people like to call the user program the mutator. See, I don't know, this thing, I don't know what it does, it mutates stuff. So you have like the GC and the mutator running in alternate slices. And then the question is like, what are you actually supposed to collect, right? If I am like in the middle of the marking phase and new stuff gets allocated, like do I just have to keep on marking to catch all the new things that are allocated? So in this kind of collector, the answer is no. The snapshot at the beginning property means that you are going to guarantee that you collect everything that was unreachable at the beginning. But if new things that are allocated and become unreachable, you don't need to collect those. You're going to like wait until some future mark to capture them. There are some trade-offs of this particular design, but one nice thing about it is you sort of get a kind of a guarantee that the mark phase will eventually end, right? Otherwise, you could imagine like doing stuff where like you keep on allocating stuff and the mark phase just kind of gets stretched out indefinitely. Okay, runtime 4. Let's talk about runtime 5. So first of all, mostly the same. Like the design is fairly conservative and tries to keep a lot of the properties of the original one. It's not sequential anymore. That's different. It's parallel now. And another thing that's interesting about the parallel design, and I'm going to talk about a lot of interesting aspects of the garbage collection here, but mostly not really about the parallel algorithms. I'm going to talk not about the interesting part, like all the other things that have gone wrong. But an important thing to know about this collector is it has a couple of different stop the world phases where all of the different threads of execution that are running, and you basically have one kind of thread of execution per core on your system. They all kind of have to check in together to do something. And there's like different things at different spots where they need to do that. And in order to make sure that happens, you have to actually make sure that the individual threads of executions will pretty frequently be able to stop and safely kind of checkpoint their behavior and check in and maybe do something else. And so as part of that, there's a kind of compiler analysis where you basically insert into the code things that make sure that you will basically always have safe points in any execution. So like, morally speaking, every time there's a loop, somewhere in that loop, you have to introduce a safe point, right? And that's basically to make sure that the synchronizations are actually efficient. So that's one part of the design. So there's a minor heap. How's the minor heap different? Well, there's not one minor heap. There are many minor heaps. There's one minor heap per core. Like you have like one heavyweight thread per core and one minor heap there. And I won't go into the details of exactly how it works, but you kind of don't allow like arbitrary edges between different minor heaps. The key point here is minor heap allocation needs to remain dirt cheap. And to do that, you want to reduce the amount of like contention and communication around the minor heaps. So like stuff that's really shared is going to be in the major heap, and stuff that's not really shared can stay in the minor heap, and you can have this incredibly efficient allocation for it. And we're going to do one stop the world collection at the level of the minor heap. So like when any single core gets to the end of its minor heap, they're all going to come together and do the minor collections at the same time. You might wonder, what if they are like have different allocation patterns, have different amounts of memory, that different amounts of work that they need to do, different amount of promotions and stuff? And the answer is, it's no problem. If one of them finishes early, it will just spend some time doing major collections, waiting for the other ones to finish up. So you're going to use all the time, but you're going to wait until the longest minor collection is finished. And there's a major heap, one major heap for the entire system. It's shared. And it has, interestingly, a kind of merged mark sweep design. One of the concerns that people were worried about in the original paper is that these synchronizations are expensive. And this is a design that goes to an older paper for what's called the very concurrent garbage collector. And it's like a cute trick where and which I'll talk about more in a second, where you can like sort of run the mark and sweep stuff together without having an extra synchronization to like explicitly end the mark and the sweep phase. You're just going to kind of do one thing to end a unified mark sweep phase. And again, a stop the world sync at cycle end. And that's to kind of play around with the colors. And I'll talk about the details of how that works in just a sec. So yeah, let's go back and talk about colors now. So first of all, what happens with the colors in runtime 4? It's fairly simple. There's the marking phase, which takes unmarked things and moves them to marked, right? And then there is the sweeping phase, which takes things that are unmarked and moves them to free, and actually takes marked and moves them to unmarked. So I should have like an extra spot in that slide, which I forgot to put in. But anyway, that's what the transitions have to do. In runtime 5, it's different. There's an extra color. So we're going to have 4 different states. There's marked, unmarked, garbage, and free. The marking phase is going to move unmarked to marked. The sweeping phase is going to move garbage to free. So there's 2 things to notice about this. First of all, it's cool. You can clearly run marking and sweeping concurrently because they don't touch the same nodes, right? The colors are disjoint. Also, it's weird because you need to like things have to get marked and then swept. So there's no interaction between the 2. That's not okay. So there's an extra color change. Oh, that's sad. Why did that happen? Sorry. There we go. This is the wages of doing a weird terminal-based presentation software. So there's a trick that happens at the end of a cycle where everyone's synchronized. This is the synchronization point, and then you swap the 3 colors. Everything that's marked becomes unmarked, unmarked becomes garbage, garbage becomes marked, and that's what links the 2 things together. But you don't do this by walking the heap. What you do is you do it by changing the interpretation of the bits that you use to mark objects. So you have like a constant amount of space that basically represents the mapping between the bitmaps and their meanings. And you just like, everyone syncs together and just like changes the meaning of the bits and off they go. So it's an extremely cheap synchronization. All right, so that's the system, more or less. There are lots of other details, some of which I don't actually know if you ask at the end, but like, there's a bunch of other details of how it works, but like, that's what's sort of mostly relevant to the story I want to tell today. So how did it actually work? So we actually ran a bunch of tests and found a bunch of regressions. Remember I said there's like a trade-off. Sometimes you can be faster in CPU terms and you be worse in memory, and sometimes you can be worse in memory and faster in CPU terms. This was kind of worse in both. There were some programs that were running 10 to 20% slower. You may have noticed 10% is larger than 3%. That's not great. And some programs were using 10 to 20% more memory. And actually, as we dug in more, there were worse regressions than that. But this, we found these pretty early and we were not happy. And then there were a bunch of sources of what caused these that we found over time. And there's another version of this talk where I go in detail about the story of how we discovered all of this crazy stuff. But I think that would be like a 3-hour talk, so we're not going to do that one. Suffice it to say, it was enormously painful to like figure out and discover all these problems. But like a few different things that went wrong. There were problems with the pacing of the GC. So when you talk about pacing in its GC, it's like the speed with which you run the garbage collector versus letting the mutator run. How many cycles do you spend on the collector? And the pacing was off in ways that turned out to be important. Another thing is transparent huge pages. It turns out, when God created Unix in the 1970s, like page sizes were 4K, and it was going to be good enough for everyone, except it's actually a terrible idea on modern hardware, and you need much bigger pages. And there's a whole complicated system in Linux for transparently giving you the huge pages you need, except when it doesn't. Anyway, for various reasons, it was like implicit. It's all implicit. The transparent, you should always be worried about things that will implicitly do the right thing for you, because then sometimes they don't. So anyway, there was a bunch of complicated stuff where we just, in the new version, the old version was built before transparent huge pages existed. And so it worked well with transparent huge pages. And the new version was built after we'd had them for a long time and it didn't. So like that was a problem to figure out. There's like the old legacy systhread system, another kind of threading system that wasn't parallel, but was threads. And like context switching was painfully slow there, and that turned out to be a problem. There are these stack checks. There's a whole new algebraic effect system for doing like fine-grained parallels, fine-grained tracking of threadlets, essentially, on top of that kind of heavyweight system threads. And that involved a new kind of check for when you're over the edge of your stack, and that turned out to be slow. And then there was just kind of a general lack of optimization in the code. Like the code just wasn't as like beaten to death and optimized as the old version, and that came up in a bunch of ways. So I do not have time to talk about all of this, so I'm going to talk about pacing, right? There's a bunch of stuff we learned about pacing, and I'm going to cover most of that. So again, let's talk about pacing in runtime 4 first, how that works. So there are two, we're going to talk about allocations on the heap, on the managed heap, and allocations off the heap, which it turns out are managed differently. So anytime you build a garbage collector, you need to decide how will users express how they want the garbage collector to make the trade-off between compute and space. So like the classic, like go back and read like a GC paper, enough years ago, it's always about Java, because that's like what for a long time all the papers were about. And the basic model was a roofline model. You're like, how should I tell how fast I am? Well, here's the upper bound of memory you're allowed to use. And when you get closer to that, you better work harder to collect. This, I think, kind of makes sense if the thing you're doing is like enterprise style. I'm going to run a single big program on a single box and it has a fixed amount of memory. This is not kind of totally how we live our lives. We have like lots of different little programs of different sizes. And the roofline model is kind of insane for that because you don't know how much memory it needs. You don't know, what you really want is for it to not waste too much memory. And so instead, OCaml is tuned via a parameter called space overhead, which tells you essentially the percentage of space that you're allowed to waste, right? Can I use 30% extra, 60% extra, 120% extra? That's the basic parameter that you're controlling. Which I think is like a good design choice. I think that's actually like kind of mostly better than the thing that Java did historically. Although, lots of GCs have evolved and have many more tuning parameters. And then we did a bunch of analysis, not we, Damien Doliger, who wrote the original garbage collector, did a bunch of analysis based on a steady state assumption. And what the steady state assumption in a garbage collector is like, if you imagine like a long-lived program, how much stuff is it collecting? Well, probably about as much as it's allocating, right? Because otherwise the memory usage is going to kind of keep on growing infinitely, like if those things aren't in balance. So the steady state assumption basically says, what happens if we just assume that we need to collect as much as we allocate? And what's cool about this is it just lets you solve problems with high school algebra. You just have like a bunch of equations about what things need to do and how many bytes you need to collect and whatever. And you can just derive a number. Turns out just like a constant that tells you like for every byte that you allocate, there's a certain amount of bytes of sweeping and a certain amount of bytes of marking that you need to do. Basically, per word that gets promoted to the major heap. So we're saying you should only clock the major heap based on promotions to the major heap. The minor heap doesn't matter, right? Like there really are two separate garbage collectors with a kind of connection between them, right? And the pacing story is very different between them. So that's the on-heap story. The off-heap story is very different. So what do I mean by off-heap? I mean like I want to allocate a region of memory. We have a thing called a big string in OCaml, which is basically a malloc piece of C memory, which we want it to be like C memory because we want to do it for like, use it for IO, and we don't want it to be moved by the garbage collector. So it could be that kind of thing. It could be like you have some library using PyTorch and it like allocates objects. It's like anything where some foreign system is allocating memory for you that you're going to be responsible for. So you're responsible for in the sense that there's going to be something on the OCaml heap that has like a handle to the off-heap memory. And so you do really want to drive the speed of the on-heap collector in a way that is responsive to the amount of off-heap memory, because the doing the on-heap collection will cause you to recover the handle to the off-heap memory and eventually collect it back. So if you're sort of ignoring, oh, I have all this enormous like off-heap stuff I'm allocating and it doesn't make you work any harder, then you're just going to like run out of memory. You're going to So how does the off-heap collector work? So the basic idea is there's a new number called extra heap resources. Think of it as a number that goes from 0 to 1. And when it gets to 1, it means you should do an extra cycle. You should do some extra work to collect those. And then there's just an equation that tells you how much you should increment by the number by every time you do an off-heap allocation. And this is n over k times h. So n is the amount you just allocated off-heap. H is the size of your ordinary heap. And k is like some tuning constant that came, from, I don't remember, working out some algebra or something like of how much work you need to do for each one of those. And like you can get like a sense of why this is sensible. Kind of heuristically, it's like, if I'm allocating stuff that's like about as big as my heap, that means like I really want to do more collection of that heap and like get to the end of a whole cycle so I can actually collect things. And so it seems kind of plausible. If you want to know what's the deeper reason that it works beyond this kind of vague plausibility, I'm going to have to disappoint you because it actually works very badly. Turns out it's like not a good heuristic. But it is the thing that people kind of came up with and was there for a long time. So that's runtime 4. A thing I want to mention about this is we're now kind of get into like control theory land, right? We have these equations that are telling us how our system should respond to its own behavior. And there are kind of two kinds of control systems that you can run into. There are open loop systems, where an open loop system is where your decisions are driven by observations of the world, but those observations are not influenced by your decision. You're just kind of watching something exogenous and making choices about it. And what's nice about open loop systems is they tend to be kind of predictable. Their behavior is easy to understand and easy to tune. And what's bad about them is they're not necessarily good at actually hitting the target that you're aiming for, because they can't see the target you're aiming for. Because the target you're aiming for is definitely something affected by your decisions, right? Because you're aiming for it. So sometimes you end up with what are called closed loop control systems. And there, with a closed control system, you end up looking at things that you are yourself influencing. And then you can like hit the target right on the nose. But I don't know, for those of you who've done like high school robotics or something, you're in PID controller hell. Like you are like trying to tune parameters. And if you like are too aggressive about getting to something, you end up like oscillating around the result. And if you're not aggressive enough, it takes you too long to converge. And like, it's just like not a great experience to like tune these systems to be just right in a wide variety of cases. And the kind of end result for this design is that if you look at the pacing for things allocated on the heap, is open loop, which is kind of the good kind of thing, at least for a garbage collector. And the off-heap pacing is closed loop. It's closed loop because of that H. The capital H is looking at a value that you are yourself influencing its behavior. All right. So that's the kind of pacing story. Let's talk about what the results look like. And in particular, so I'm going to show this graph where on the x-axis, we have the space overhead we requested, right? We told the system, give me a space overhead of 30 or 100 or whatever. And I actually don't remember even what these numbers exactly mean, but like this is some way of expressing that like percentage overhead that you get. And then on the y-axis, you just measure it. You look at what the program actually does. And like the black line in the middle is the thing you would like to approximate, right? You want to get what you requested, right? So how did it actually work in runtime 4? And the answer is like mixed, depending on the benchmark. So there are like 3 different benchmarks here. The ones that are like looking pretty close to the black line are programs that are doing a lot of ordinary heap allocations. And then the one that looks insane, that's like totally flat, nowhere near the line, is one that's very aggressively doing off heap, like quickly cycling through lots of off heap allocations. And that one, you can see what's happening is the garbage collector is just working insanely hard, right? So that's how runtime 4 looks. That's how it's behavioral. Now let's talk about what's the design of runtime 5 and how does that work? And then how does that change our behavior? And I guess just to go back for the second, that line on the bottom is a serious problem. Like we use a lot of off heap memory. It totally screws up the tuning of the garbage collector. And we've had to do a lot of annoying work to kind of adapt the behavior of our programs to this misbehavior of the garbage collector. So this is like a thing that we have tweaked and adjusted and tried to fix for a long time. Okay, runtime 5. How does that work? So the pacing approach for ordinary allocations is just the same. In general, like one of the nice things about the original paper is it's a very conservative design. It tries and successfully preserves a lot of good decisions from the original collection. But it did fix a bunch of implementation bugs with respect to off-heap memory in particular. For example, one stupid, simple thing that was wrong in the implementation of the off-heap thing is the off-heap collections were driven not by promoted memory, but by even if you like if I allocated onto the minor heap a thing that was pointed to off-heap memory, and then it got collected and never made it to the major heap, I would still affect the clocking. So that makes it like massively way more aggressive than it should be. That wasn't the only bug. There were a bunch of bugs. There were a bunch of bugs like, mutually opposing bugs. Some bugs in this direction, some bugs in that direction. And when you're in a system like this, where you have like this runtime behavior, it's got various different exciting bugs, and then you're building, you're spending 20 years building lots of programs that operate in the system, the bugs become load bearing, right? Because everyone has adapted to the behavior of the system, and like, you should be a little worried when you fix the bugs. So what happened when we added runtime 5? So here's the picture with the runtime 4 lines. So much better. So like the lines that are going up super high, these are ones that are using massively more memory. These are the ones with the ordinary heap allocations. And then like this kind of like way too flat red line, like that's better. It's like less, it's like closer kind of to the black line. And that's mostly better because of like the bug we fixed with allocations on the minor heap. So that particular benchmark is very sensitive to it. And so the behavior is much better there. But like, this is not good. And we didn't like quite understand what was going on here. So what was going on? So it basically turns out that ordinary collection in the new collector is just less aggressive. And in particular, the unified mark and sweep design that we stole from the very concurrent garbage collector turns out to be a lot less aggressive at capturing all of the garbage you need. And in particular, there's this problem what's called floating garbage, charmingly in the literature, which is like stuff that was allocated, but can't yet be collected because of this like snapshot at the beginning thing. It's like, it's going to be collected in some future thing, so it gets delayed till farther off. So let's visualize a little bit what's going on here. My second vibe-coded visualization here. So here, what would happen in runtime 4, you have these sequence of like sweep mark, sweep mark, sweep mark segments. And of course, like a good garbage collection analysis, I don't even bother putting the program in there. The mutator is not worth talking about. We just like garbage collectors. So what happens when a thing gets allocated in the middle of a sweep? Well, at the end of the next mark phase, you will have proven that it is not reachable. And then in the middle of the next sweep phase, somewhere in there, you're going to get the chance to actually move it to be free. So that's going to take you like one merge sweep mark cycle on average to get to. What happens if I allocate something in the mark phase? Well, because of the snapshot at the beginning thing, it's not going to get marked by the end of this mark phase. So you really need to wait till the next mark phase, and then you can only collect it in the sweep phase after that. So now you're going to spend a cycle and a half doing that. Okay, so far so good. Let's look at runtime 5. Now we have these merged sweep mark phases. And it's worth saying in this design, even though you sort of don't need to synchronize, the sweeping is mostly at the beginning and the marking is mostly at the end. So we can sort of ask the same question of, if I do an allocation in the kind of sweepy part of the sweep mark phase, when does that get collected? Well, I have to wait till, it can't get marked until like the end of, I have to wait till like the next big sweep mark phase to actually mark it, and then the next sweep phase after that to actually collect it. So I'm going to wait a full 2 cycles to get it. On the other hand, if I allocate something during the mark part of the sweep mark phase, that sort of ends at the same point, but that's actually, so like the thing that was 1.5 cycles is still 1.5 cycles, but the thing that was 1 cycle is now 2. And so we go from like an average of like 1.25 cycles to 1.75. And so it's just a lot slower, right? So that's the problem. Which like didn't exactly, like this wasn't not known to the people who worked on the original paper. And it was actually the people who worked on the original paper and the people who worked on fixing it up are like the same people, some of them, right? So there's a lot of conservation of thought between the different phases of this work. So anyway, that was a problem that we worked through and we just fixed it. Like we came up with this mark delay patch, which basically didn't like totally give up on all the design aspects of the nice VCGC thing, but it was like, actually, we have discovered as we've been doing experiments, these synchronizations that we thought were super expensive are actually pretty cheap in practice. And having another one is just kind of not a problem. And so it adds another synchronization into the system and it recovers the old kind of behavior for what the lifetime of objects is. But as I said, like the excessive collection with big string story is still better in this than the other because of like the bugs we fixed. So as I said, all right, one bug fix made things less aggressive, others made it more aggressive. So what do we do next? Well, let's see what the results are of the mark delay patch. So again, here's the picture. The yellow is runtime 4. The red is like the original version of runtime 5. The green is with mark delay fixed. And like, it's a mixed story, right? So first of all, it's still kind of veering kind of far from the black line for the ones that are like doing heap allocations, but it's better. And the off heap stuff is worse because in general, fixing the mark delay thing makes collection become more aggressive. So that kind of pushes that part in the wrong direction. So that's not awesome. So what did we try next? So we'd spent a bunch of time fixing the implementation bugs. We thought, let's maybe fix some of the design bugs, right? So one of the design bugs is that like N over KH kind of uses the wrong notion of H. Like the weird pathological case turns out to be where you're like doing a lot of off heap allocations, but your heap is really small. So this ratio gets totally blown out. And now you just want to super aggressively collect all the time. It would be better for the H to be the sum of the two, the off heap plus the on heap. So we worked on that and we kind of improved it and it seemed a little bit better. But now we started running into this like closed loop control system problem, which is like, we could get the behavior a little better, but we were like, had these like, you know, oscillation tuning problems and stuff. So we weren't super happy about it. So we kind of went back to the drawing board and just thought like, okay, like, can we just design something more unified that's better, that does the whole thing? And we basically rethought the steady state analysis, pulling in both the off heap and the on heap stuff into the same set of equations and working through the high school algebra. And like, kind of surprisingly, it worked. Like, it's one of these things, like you throw a bunch of equations, like there's no deep reason that we know that it had to work, but like you throw the equations together and like, you know, things like capital H that are the things you don't want to depend on, like they still canceled out. So we ended up with a system that basically, again, had a constant number of words collected per word allocated, and you didn't have to look at the state of the heap. And the difference is you had to do, the difference between on heap and off heap allocations is that when you did an on heap allocation, you needed one extra byte of sweeping work to be done, which kind of makes sense, right? Because like the on heap stuff you allocated has to get swept and the off heap stuff does not have to get swept, right? So that kind of makes sense. So how does the design work? Well, turns out kind of shockingly well. I don't know, like the sense of relief I get from looking at the blue lines on here is hard to convey. It's just like so much better and simpler and easier to reason about. And like, it just kind of gets rid of this problem that we have had for years fighting over of trying to deal with how to handle off-heap memory in a better way. So that's kind of mostly the end of the things that we learned about pacing. There's a couple of other interesting things coming out. There's like some new experiments about like trying to like tune the thing a little bit away from a pure steady state analysis so that you can, it turns out programs have a property where often early on in the program, you're allocating lots of stuff that isn't going to go away soon. You're kind of doing setup of your initial program and like the things you're allocating are mostly going to stick around, and doing a lot of garbage collection then is actually kind of a waste of time because you're not going to collect anything. And so there's some new ideas about tuning that behavior so that like you do less allocation there and you do less collection there and those things are more efficient. But like the big result was this thing, was kind of getting all this stuff in line. So I want to talk a little bit about like what we learned from this whole process, not just the process of like disentangling the pacing stuff, but in general, working through this like long and complicated set of problems that we ran into in getting the runtime to work. So one of them is benchmarking is hard. And I think the original paper just leaned too much into the thing that like papers often do of like, what benchmarks should we run? You know, some of the standard benchmarks and like the benchmarks that are easy to run. And that ended up pushing them in the direction of testing a bunch of relatively small programs that just didn't like embody a wide enough set of the potential different possible kind of program behaviors that you needed to do to see when things went wrong. And so being able to see more of those use cases, I think was important and sort of exposed different problems in the system. I think actually one interesting corner of like why they did this is they had a good idea that caused them to do a bad thing. The good idea is long-term, there should just be one runtime. I think that was a good idea. The bad idea was to start off with OCaml 5 only having the one runtime and OCaml 4 only having the other runtime, because it meant it was really hard to benchmark the two runtimes against each other. And one of the first things that we did was to backport, so we had both runtimes with the same language. So we sort of had the first opportunity to do kind of like for like comparisons on real world programs. And I think they should have prioritized, and again, when I say us and they, same people to a large degree, we should have collectively, and also not me, I just, you know, I'm just good at talking about what other people do. But like I think it would have been really valuable to have more of that early evaluation to be on larger scale programs. I think more of these problems would have been discovered early. Another thing is once you benchmark and find out there are problems, debugging the problems is hard. So like I showed you one issue, there were like a dozen issues, and like the bugs cover each other over. Like the worst performance bug makes it hard to see all the other ones, but you actually, you know, Pokemon, you got to get them all. You got to like figure out how to get all of these different things. And then the other thing that we did is like we would find a problem and be like, this is the biggest problem, let's fix it. And then we would develop a good solution to the problem. And that was a mistake. We should have developed bad solutions to the problems, because you can develop a bad prototype solution much more quickly and discover, is this problem actually the important one? We were like doing too much high quality software engineering and not enough like experimental poking at things. And we also should have spent more time like dealing with this, like the problems covering each other thing of like creating small focused benchmarks that exposed in a clear way the different misbehaviors of the system so that we could spend more time focusing and iterating on fixing those individual misbehaviors. Another thing you learn is like sometimes you should like go back to the drawing board, right? I think it's very tempting and often the right thing to do to just like incrementally try and fix the thing that you're working on. It's like the system, it pretty much works. Maybe, you know, yeah, runtime 4 was broken. It's been broken for a long time. Somehow here we are, still a running company, things are working. We don't have to fix that problem. Maybe we can just like make it kind of work. And in this case, it was like, no, actually don't make it kind of work. It turns out sometimes you need to go and get a first principles, like rethink the whole thing, and maybe there's something fundamentally better available. And in this case, we got one, and that was very satisfying. Also, backwards compatibility is really hard, right? You know, every time you change something, somebody's workflow gets broken. You know, all of, you know, the load-bearing bug problem is like a really serious problem. Like, you know, you have all these things that have been tweaked to kind of behave in an okay way based on the system as it works. And then being able to roll out the fixes may break lots of production systems. And so there's just a problem that you have to think really hard about. So that was a long story about a nice paper with some good research and good ideas and the painful set of realizations as you try and bring that into production. We're doing that again. So there's a nice paper called Data Erase Freedom a la Mode. It won the Distinguished Paper Award at Popple in 2025. And this is about, in some sense, the second half of the parallelism problem. Part one is a runtime capability. I can run parallel shared memory programs, but without a programming model, right? You know, you're just in like mutex, semaphore, condition variable hell, like good luck, right? And we were not particularly satisfied with that. And so a lot of work went into finding a bunch of type level guarantees that we could, kind of new type system extensions that would allow us to write programs where you would get a proof from the type system that your program is data race free. And then we've done a lot of work to make that happen. One piece of the work is propagating that type information through our libraries. Like one example of a new thing you can decorate on a file, on a function, is that it's portable. It means you're allowed to like move it to another core and run it on that other core. So you have to like do a bunch of like, big refactor stuff to write these annotations in the right places. You'd think that was the hard work, but the actual hard work is fixing the data races. Turns out, if you have a type level discipline for discovering data races and an old code base that does a lot of stuff, even what is supposedly a nice functional programming language like OCaml, you'll discover a lot of like dirty tricks and immutable state and all sorts of stuff where you didn't expect or remember that it was there. And like the type discipline works and we discover a lot of these bugs. And by the way, as a small aside, I have no idea what Python is going to do, right? There's this new free threaded Python thing coming, and like, it's a runtime capability, and I don't know what their programming model is going to be and how they will like survive as like they try and do more. I think I kind of mentioned to someone earlier, I think, they'll probably just YOLO at some and be like, yeah, there's some data races. Python programs break for lots of reasons. Like, but I don't know, it seems hard. We're building lots of high performance data structures. We're doing all sorts of interesting work on user level scheduling. I sometimes like to say there's like 4 or 5 things that are terrible about writing parallel programs. One is like it's hard to avoid data races. One is it's hard to pick the granularity of the job that you want to parallelize. You pick it too small, you get swallowed by overhead. You pick it too big, you can't use all your parallelism. So that's annoying. One is it's hard to like actually pick the amount of concurrency you want, how many concurrent threads you want. So we're like taking some ideas from the literature, stuff called heartbeat scheduling and various other kind of like control system things about how to kind of dynamically adapt the amount of parallelism to build smart schedulers that mean that users can just like describe things in a natural way and stuff will like just work pretty well. Another bad thing about parallel programming is it's hard to know why your program isn't working fast. Why it's not fast. You got it to work, but like, why is it slow? And trying to build profiling analysis tools, because like just parallel systems are like really unintuitive, and like you have a shared memory system, but you don't really. There's like cache lines getting shared left and right, and it's actually much harder to understand than you think, and trying to like build tools that help people understand it. And then also building new abstractions for efficiently and ergonomically combining parallelism and concurrency. And here, by parallelism is where you like offer up to the system, here are a bunch of things, you should feel free to run them in parallel if it'll make it go faster. Concurrency is where you're like, here's a bunch of things, these can't block each other. I'm demanding that they run in parallel. It's actually, these kind of are like duals to each other, and they're like complicated to integrate into a single system and a single scheduler. And we're trying to build good systems that I think do that in a way that's kind of better than anything that we've seen out there. And then of course, there's teaching people how to use all this stuff, right? There's a lot of new ideas and new stuff going on, and like, there's a lot of teaching that'll need to happen. So like, stay tuned. Maybe I'll come back in a few years and write a paper about how this was dramatically harder than we expected. But we are working actively on this stuff, and actually a lot of this is like in the process of becoming more public. So all of this work on the OCaml compiler, both stuff we do directly upstream and stuff that we do on our own branch, like all of this is intended long-term to be upstream. But long-term, I think it's a process that takes years. And we wanted to take the stuff we built and make it more available for people to look at. So we are like publishing, actually on Friday, we can go to OCaml.org. So we've named, like if you want people to know what a thing is, you got to give it a name. So we've called it OCaml, OCaml oxidized. And it is going to like officially show up on Friday. There'll be like a website and, believe it or not, actual documentation and the ability to like install a compiler with like an LSP that works and a formatter and the tools all fitting together. So we don't like this. OCaml is sort of in an interesting state. It is like totally a production ready compiler. It's our production compiler. We use it all the time, but it's not really meant for other people to use as their like production compiler for like real stuff, because we are going to like break your stuff mercilessly all the time. Like it's going to be, the OCaml stuff is going to be compatible and all of that, but like the extensions, we're just like iterating really fast and taking advantage of the fact that we control our own internal system, and like we can automatically refactor stuff and get it kind of lined up. for the outside world, I think it's great to experiment with. You're like a researcher or an enthusiast, and the code base you're doing is relatively small, but it's not like a real stable language for like a community, a kind of big, practical community to build itself around. But we think it's exciting, and we, invite people to kind of check it out when it lands just, at 9:30 p.m. on Friday, I am told. And that's all I've got. So thank you guys very much. All right, so now I think we're moving to questions. So there are people with mics. Folks should raise your hands.
Oh, hi, amazing talk. I think one question I have, and I see this around in Hacker News and Reddit, is that I'm curious why Jane Street chose to go with OCaml when, like, it's a garbage collector language. So, you have to build in your own garbage collection mechanism. And I'm curious also, like, that's the first part of the question. So, like, why going with OCaml? And second part of the question is, like, what do you think about a new, like, maybe Rust, where they have, like, the ownership model? It's a different way to manage memory. Yeah. So, and in general, for high performance computing, like, do you think that's the way forward?
Yeah, so I think, at the time that I think Rust is like the interesting other language that one could have picked. Say an obvious thing, at the time that we picked OCaml, Rust did not exist. So it's not like a plausible thing to pick. Rust, by the way, was written in OCaml. So obviously OCaml came first. But when I think about it today, I actually think OCaml is a better language, specifically maybe to say, I think OCaml is a better language for the kind of work that we do than Rust. I think the key advantage of this version of OCaml, of OCaml, is it's kind of a broad spectrum language. It has the kind of lightweight ease of use that you get from the kind of simpler discipline of a garbage collected language. And it has optional, when you need it, gradual control. So the kind of ownership things you're talking about, we actually have in OCaml, like things like uniqueness and linearity and things like that are actually part of the system. We have a thing called a mode, a local mode, where values under the local mode can be allocated in a type-safe way on the stack. So you get a lot of the same kinds of control over memory that you get in Rust, but you get it in a gradual way where you get to pay for it when you want. Rust is very much pay up front. Welcome to the door. You will welcome to your undecidable type inference problems and annotations all over the place and being explicit about memory management everywhere. And actually, especially in parallel programming, there's a bunch of patterns, like very efficient patterns, and are just much easier to express and more efficient to express in a system with a garbage collector. If you want a bunch of threads that are going to share some kind of mutex protected state, who's going to own that, right? The ownership discipline is really hard. Whereas one of the great things about the OCaml design is that you get the control where you need it, but you can also just use the garbage collector in the cases where that makes sense. And we build lots of what we call zero alloc systems in OCaml. And zero alloc systems don't literally do no heap allocation, but they'll typically do no heap allocation in the type loop of the program. And the extensions that we're doing make it easier and more natural to do that kind of thing. And that is actually important. in some sense, you don't have a lot of choice. If you want to build a high performance packet processor that will consume and emit a packet in 1.2 mics or something, your program can only behave in one way. It will you'll DMA stuff into memory, you'll read some things, maybe you'll mutate some stuff, you might send some stuff out, but you will not allocate a thing on the heap or create a future representing, it's gotta be this very, very simple physical structure. But I think the language that OCaml is developing into here gives you a really good way of writing those kinds of programs while still being the same language that lets you write a lot of other kinds of things that are much more expressive and easy and lightweight to do. So I don't know, it's a long, I certainly didn't choose OCaml because of the things that we're doing now, but I feel overall, it actually has worked out very well. In part, we're building the things necessary to make it work out.
Thanks for the talk. Operationally, I saw that you said runtime 5 was GA.
Yeah, general availability is what I mean, yeah.
So I presume that it's rolled out in Jane Street? Or...
Yes. It's not rolled out for every single application. There are some applications that have seen some regressions that have held back, and we're still kind of digging through some of the final problems. So like there is like an addendum to the talk that you can imagine in the future as we figure some more things out.
Right. So my question was like, how did you control that rollout in terms of like, there's a performance side of things which we talked about, but I guess there's also like the correctness.
Fire in the hole.
Bits,
like,
right. How do you make sure that, how do you monitor for that?
So, I mean, we did a bunch of testing and we just kind of turned it on and then said, you should look carefully at how the performance is. And if it's a problem, here's how you roll it back. So there was some discussion about whether this was the right choice, but this is in the end what we did. It was possible to do other things, but we felt like this in the end was simpler. And you got a bunch of incremental rollout just because not everybody rolls on the same day. Like you release it to the tip of production, but like, it rolls out over a few days, people discover things. It's worth saying we tried an earlier rollout that went very badly. And we're like, never mind, and we switched it back. So it's not a foolproof system for sure. Thanks. Oh, sorry.
Yeah, great talk. So I have one question. You said that the minor heaps are per core, but the major heap is shared, right?
Correct.
Okay. So if that's the case, then so I was just thinking, how do you prevent contention and shared shenanigans when you promote it to the major heap? Because once you promote it to the major heap, it's shared across cores, so you usually get contention from that. Unless, you just assume the generational hypothesis is true and you just, let it.
So I'm not totally sure I understand the question. If you're saying like, I mean, when you say how do you avoid contention in the major heap, do you mean in the garbage collection algorithm or do you mean from the mutator accessing data in the major heap? I mean, the answer is you write your program in a good way that there's not too much. I mean, this is like, on my like 5 reasons why parallel programming is hard, one of them is predicting the behavior of parallel programs is hard and knowing when there's contention and when you're sharing cache lines back and forth, whatever, is hard. But I feel like if you would like to use modern hardware, this is just not a problem you get to avoid. And maybe there's some smarter static discipline that would let you write programs where you could predict and know when you're going to get contention. But like, I kind of don't think it's very likely. Like if you look at the academic research on static resource analysis, it's like really fairly primitive what you can get out of it. So I'm like fairly dubious that there's a good discipline that like statically gives you what you want there. But anyway, we have no good answer to this question other than like, learn how to write good parallel programs.
Hello. Yeah, nice talk. Just like to ask you, what are the things you are doing to, apart from, the type making your programs safe in general, are there any other thing that you do to, try to give stronger properties or stronger guarantees, either in the concurrent programming setting? Have you moved more into dependent type, for example?
Right. So these are clearly questions from the formal verification part of the audience. So we do surprisingly little formal verification. A few places where it comes up at Jane Street is like, we do a bunch of like hardware synthesis work, and there are places there. I mean, one thing that's nice about hardware programs is that they are more static than ordinary programs. And so static analysis tends to be more tractable, and simpler kind of SAT solving and SMT solving and whatever techniques are more effective there. We do very little that's like full-on theorem provery stuff, like almost nothing that has that shape. Like, the paper the data race freedom LMO paper had some of that kind of analysis in there, but like, that was Derek Dreyer's group doing it. That was not us. And it's not for lack of an understanding of it. There are like people on the compilers team who like, write proofs and cook, for recreation on the weekends. But we have not found it to be kind of valuable enough compared to the cost for reducing error rates. So just like if you look at like where our bugs are, it's just like not in the kinds of places where this kind of formal analysis helps that much. It's not totally true. There's like C bindings is a place where we built some static analysis tools. When we're writing like compiler optimizations, it's like no human knows how floating point operations work, but Z3 does. And so it's like nice to ask Z3 whether or not it's a sound optimization. And there's various places like that. But like we tend to rely on more traditional things like very careful testing. There are some of our key systems are like risk analysis systems where we'll basically build a kind of second implementation as a reference monitor to the first one to kind of catch errors in the system by having one monitor the other. But very little that kind of looks kind of proof theoretic in structure. obviously outside of like the type system itself, which is of course a lightweight formal method. Right.
Interesting talk. So I think you touched on this at the end of your talk about kind of program setup and teardown. So is there any way for, is there a lot of work being done on kind of smart allocation, something like processor branch prediction and things like that? So can you, I think you mentioned that kind of more recent objects get freed pretty, they don't live that long, right? Is there any way to preserve, like to predict how long kind of items stay around for, basically?
So the basic stupid trick that people are looking at now is to use the percentage of the minor heap that is promoted essentially as a heuristic for thinking about how long stuff is sticking around. So when a very large fraction of your minor heap is promoted, roughly the intuition is this suggests that this stuff is not immediately going to be collected. And so you sort of reduce the pacing rate when you are in the state of doing that. So that's like, there's like, this is work by Stephen Dolan and Nick Barnes at JStreet. Like Stephen has like come up with like 3 different ways of thinking about what the equation should work out to be. And they all kind of point at the same particular heuristic. And so we sort of feel like it really kind of makes some fundamental sense, but the actual thing it's doing is kind of rock stupid. And we are hopeful that will be a pretty good way of making it. It's like a real problem. Like I saw earlier today on some Slack channel, someone being like, my program is really slow on startup because it's allocating this stuff. What can I do? And the answer is like, you can turn down the space overhead during the startup range and turn it back up after you're done. And it would be lovely if that just happened automatically. And we have some hopes that the new pacing thing will in fact do a good job of that.
Yeah. Thank you for the talk. It's been really good. I think one of the interesting areas of GC research at the moment tends to be concurrent collectors, where the mutator is running at the same time as the garbage collector. And obviously a lot of what's driven us towards that is the kind of soft real-time requirements in finance and wanting to trade off a little bit of throughput for lower latency. So it's somewhat, in some ways it seems somewhat surprising for Jane Street to build a parallel garbage collector rather than a concurrent one. It'd be good to understand some of kind of the reasoning as to kind of how that happened. And
so I think there's a few points. So first of all, I think the design did not come out of a like build the fastest possible like super low latency trading system perspective. And a lot of the requirements around the particular design are around backwards compatibility, right? Not breaking C binding, something like that. I also think like I maybe not facile enough with the terminology of the field to get this right, but I think it's like a somewhat concurrent collector, which is to say a bunch of, you can like be doing a major slice on one domain and be doing ordinary work on the other. And like the actual locks, the actual like synchronizations are really quite brief. So it's like kind of a compromise between the designs. Also, no one who's writing fast trading systems is doing any garbage collection. So I don't like, no, that's not how you do it. You write 0 allocation systems if you want it to actually be deterministic and fast. So I think like there are other interesting things to do, like having like explicit separations between these are the domains that don't allocate at all. These are the domains that do, and they don't actually share a garbage collector. We have other ways of moving information between them that I think are more promising. Like I kind of think we should make, I think just the whole premise of we should make a concurrent collector for high performance trading systems is like super confused. Like, what we do when we make it really fast? We want, we like make an FPGA, right? Where there's no garbage collector running on the FPGA. Like if I would like to turn around a packet fast, like if I can't do it in under a mic on a CPU because it's like a half a mic each way over the PCI Express bus. So it's like just not going to work. If I want to do it in like under 100 nanoseconds, I'm going to do it in an FPGA that's directly wired to the NIC. And like, I don't know, it's just like, I think it's just kind of the wrong framing for the kinds of really high performance problems that we have. And maybe it's also worth saying like, there's an enormous amount that we do that is not just writing a highly deterministic low latency packet processor. And there's lots of parallelism problems that we want to solve. And so it's like, in some sense, I feel like too much of people's model of James Street is something like there's like the wire from the exchange and like back to the exchange, and like that's what a trading firm is. And like it's just like a dramatically richer and more complicated and frankly more interesting space than that extremely narrow view is. Like the number of different kinds of CS problems that we have to solve is kind of like mind-blowing. One of like I worked at James Street now for a disturbingly long time, like 23 years, and like one of the reasons it's great is that there's just like so many different kinds of problems. And so you really want really good general purpose systems that can solve a wide variety of problems, not to get hyper specialized on like just one kind of question that you need to resolve.
Hello. Yeah. So thanks for the talk. My question is more like, how do you like after realizing the performance dip, how do you like stay committed and like continue spending the next 2 years debugging instead of like going back to the drawing board, thinking like whether this might not be the right language to begin with for this your use case?
Right. So how do we like? Why did we not give up? It's a fair question. So first of all, we have like 67 million lines of OCaml code. Giving up is like not a simple thing to do. There's like a lot of value and a lot, I don't know, like you build a big company that's successful. It has all this value in the software that is built, and like it's very valuable to move it forward. And like there's just no thing that is removing a programming language from a company. Like you can kill the company, that can get rid of it, but like faith.
It could be like building it in parallel, like so you have a very new features on it.
Yes, you can add a new language, which creates an enormous amount of extra cost, right? I think like we added Python, and I'm very glad that we added Python. Like basically the machine learning ecosystem is just like unbeatable and would be ridiculous to try and replicate. But like adding Rust would just be dumb. Rust isn't interesting enough or good enough or different enough. C++ isn't like enough of a value, and it's just not worth the enormous amount of work of supporting a new language well. And it's just like cheaper to improve the language you have. And like, this is not just us. You want to hear a more extreme version of it, PHP and Meta, right? PHP is like the worst language on earth, right? Like my favorite story about PHP being insane is that like the standard library has a bunch of really oddly named functions because at some point they realized that it was inefficient to have a lot of functions with the same length because their implementation had a hash table where it was hashed by strlen. So if you had lots of things of the same length, they got put into the same bucket. And then you did these linear scans over the bucket. So rather than, and the thing I love about this is like, rather than observing the problem and fixing it, they just like screwed with a standard library. So it wasn't that big of a deal. And this is the language that Facebook is built on, right? And there's millions and millions of lines of PHP. And what did they do? They did a long series of projects to make PHP an acceptable programming language, right? They have like their own PHP runtime. They had like a transpiled C++ for a while. They now have their own gradually typed version of PHP called Hack, which is of course hilariously implemented in OCaml. And like, it's just like, we're like, let's replace JavaScript. No, like we're not going to replace JavaScript. The whole world is built on it. Is it a monstrosity? Obviously, yes. It's a terribly designed programming language. Go read what Brendan Eich said about it. He's like, don't complain to me. I did it in 2 weeks. I was in a rush. Like, but here we are in the world built by Brendan Eich's 2-week hack fest to make a version that was kind of like Scheme and kind of like Self, but like they didn't have time to really get right. And like, that's one of the problems with programming language. The ecosystems are so valuable that you really end up really strongly wanting to live with it and figure out how to make it better and how to get it to work well. And so we, I think, are kind of under those same pressures and kind of responded in the same way that lots of other organizations have.
Thank you.
Hello. Yeah, thanks for the talk. My question is, you mentioned that JStreet had to revert to the previous version where you can like test out the performance of your GCs on like 2 runtimes. Sounds like this should have been the job of the researchers to test out just to compare performances. And I guess my second question maybe is like common knowledge to everyone here, but Why would you say that it's a good decision to like just support one runtime at a time? It's up.
Right. So when you say it's the job of the researcher, I would like to say, like, many of the same people worked on both sides of the problems. I feel like, I am not here to complain about the work done on the original paper. It was a great paper. The design had lots of things that worked out really well. They figured out a lot of important stuff. Most of the design remains as it was. Like, it's great work and we're grateful for it. I do think the particular idea of launching it with just one runtime available was a tactical mistake, right? I do think long-term, it is better for the maintainability of the language to have just one runtime, but I think they should have gone through a period with two and then removed the second one. And so, I don't want to blame anybody, but like, I think that was a mistake. And then we ended up like reverting that mistake for a while and figuring it out. And then, I don't know, I think in the end, everything's kind of in a good state. Most of the fixes that we've made have been upstreamed to the regular upstream OCaml. So like, there were actually lots of other users who were also discovering some of the same problems that we were running into. And these have like not 100%, but mostly been fixed broadly. So I think the outcome is good, but I do agree that was narrowly probably a mistake in the original research.
Oh, could I ask a question? Yeah, like I just want to start out by saying that's a very technically interesting talk. But I guess like my question is a bit meta, like, right? Like, what's the, Jane Street is obviously a capitalist institution. You are the CTO, your time is valuable. Like, what's the ROI for like renting out a hotel room here in Singapore, giving up this talk on this kind of obscure topic, and then taking up like 2 hours of your time? Like, yeah, what's the, is it like to nuts like people to say, oh, you know what, if you're interested in like these obscure technical stuff, maybe you can join Jane Street. Like, what's the kind of...
Sure. I should highlight, it is a pernicious rumor that I'm the CTO of Jane Street. Thankfully, I am not. Like, I'm one of the senior leaders there, but there's a lot of senior technical leaders. And we actually don't have a CTO. It's kind of not how we're organized. That aside, I don't know, like, Jane Street is a place that is driven by the people that we get to hire. And Singapore is actually kind of a great environment from a kind of tech ecosystem. There's like lots of great tech companies here and lots of great academic institutions. And we are just like looking to grow and expand. And we think by coming and giving these talks, we get to give people a sense of what are the kind of technical problems we solve, what are the things that we worry about, just to get a feel of the kind of the intellectual nature of the place and why it might be an exciting place to work. So yes, like there's lots of other nice reasons, like Chenzo was saying about like sharing ideas and all of that. But like, yes, secretly we would like to hire you. You have found us out.
In fact, there's like how much of this was like the bigger OCaml very much of this Jane Street, because I think it makes sense because the same people on both sides are
So the work that I talked about here was essentially all people inside of Jane Street. Some of them are people who also worked on the original paper. So like we've hired some of the people who worked on. So that is the mechanism by which it is the same people. But the actual work here was all stuff done inside of our walls. And it's being just a general fact that's worth saying is that like there are some kinds of PL research that are just much easier to do inside of an ecosystem like ours, because like in an open source context, like you try and like put up a PR for some big change to like the OCaml, upstream OCaml language, and like you're going to get a lot of skepticism about it, and for good reason, because like these people are long-term committed to supporting the language and its ecosystem, and like they don't want people coming in and like messing up their language and leaving stuff they have to take care of that like isn't quite right. And like, when you put out something in like the surface of your language and its API, people will use and depend on every part of it, especially the parts you didn't mean, right? And so it's very hard to make mistakes in this kind of public setting. But in this kind of internal private thing, we can iterate really fast, get lots of feedback from our 1,500 developers or whatever it is, and iterate quickly and like make mistakes and walk them back. And so when you're making really ambitious changes that are hard to do incrementally in a kind of larger and more established language, there's something kind of great about having this kind of captured internal audience. The other actually kind of crazy great thing about the Jane Street internal audience, especially if you're like a PL person who likes, types and stuff like that, is I feel like in like PL academia, you have like a good idea for a thing you want to do in a programming language. One problem is like, what's the thing you want to design? And the other is, how do I convince people to use it? Right? Because like people mostly don't want to use your weird type system stuff. And like people desperately want to use our weird type system stuff. It's kind of amazing. Like people are like angry at us for not producing it faster. And so it's just like an exciting place to kind of build these because it's really like lets people kind of level up the work that they're doing and gives them a lot more power. And it's a place that like understands the value of the tools. And so it's kind of an exciting spot to do that kind of research.
Hello, hi. So I just wanted to ask you, from an outsider's perspective, the reputation of Jane Street is OCaml purists. And I mean, working in other companies, we tend to choose languages which the business thinks of the language serving the business, right? We don't want to serve the technology. We want the technology to serve us. So for example, in Jane Street, I mean, obviously you guys are doing a machine learning in Python because it's just an amazing ecosystem for that. So I'm wondering how you guys, avoid the situation where you are serving the technology instead of the technology serving your business. Because, you're doing almost like a lot of things in OCaml instead of being flexible with your languages. Thank you.
So, I mean, I don't want to make the argument that there are no trade-offs and no downsides to using like a comically unpopular programming language, which is like for sure what we're doing. And I think the major thing that you trade away is various kinds of ecosystem benefits from the outside world, software that you can use on the outside more easily that's harder to use because you are doing something weird. And I think the initial decision to use OCaml was easier and more natural because the kinds of things we were building at first were like fairly self-contained. We were not like a web shop. We did not need to like hook into like all sorts of like weird web frameworks or whatever back in the day. We were building like, obscure like fixed processors and kind of very trading specific stuff where there was not like an interesting open source ecosystem to pivot off of anyway. So like the initial choice was driven a lot by that. But I'll say like the language from the start served the business, right? We actually started using OCaml a little bit, kind of by mistake, because like I started, first working part-time at Jane Street, writing some software that I was pretty sure was throwaway stuff. And I started writing it in Python. It was like, too painfully slow. And I rewrote it in OCaml because I thought, it's research code. It's all going to get thrown away later. And like 80,000 lines of code. And 6 months later, it wasn't getting thrown away and I wasn't going off to be a professor. And like, that was the sort of random mistaken birth of Jane Street's OCaml code base. But like over the next couple of years, we tried lots of things and we're building software in a bunch of ways. And like, we switched to OCaml because it was serving the business. It was better and faster and safer and made more money day in and day out than using Java or C# or C++ or whatever. Like those other things worked less well for the organization. And like the language has just worked super well for the business, right? I think the thing is like, why don't you do something more pragmatic? And like, I understand the critique from the outside, but like, in the circumstances we're in, it's like surprisingly pragmatic and it's like worked kind of amazingly well. And like, we're not doing it because we're OCaml purists. We're doing it because it like really works.
Yeah, thank you. Bye.
Thank you. Great talk. As you've said, Jane Street is a very specific ecosystem with a lot of very specific use cases. You battled for years to introduce these new multi-core capabilities to OCaml. What was the biggest win that you immediately saw from introducing these new capabilities to that ecosystem?
So it's a good question. We are like extremely early on the path of using it. So like I said, like I feel like the like someone asked like the multicore, the runtime 5 became like general availability like a few weeks ago. The type system level support for writing parallel programs is like also just like landing in its like form to do things in the last few weeks. And we have our first real applications using it now. But we're starting to have a sense. We've done a bunch of kind of demo applications and tried things out. There are some applications where there are like highly specialized, already highly parallel applications in some cases, but that are using other techniques other than shared memory parallelism. You might have like shared memory segments or other forms of IPC for communicating between them. And some of those we're doing like very careful and focused rewritings of those systems to use multicore, the kind of multicore style parallelism that we have in the language now. And there, we're seeing like significant like integer speedups over these already parallel systems because we can just do scheduling in much more efficient ways. Just like the whole system can just like be designed in a different and more efficient form. So there's like some things that look like that. But I think actually an enormous amount of the value is going to be doing simple, stupid stuff of like, I just want to run this fairly simple thing in parallel And like, it's not very complicated, but I want to easily absorb a bunch of parallelism to do a thing. And I think it will be relatively easy to do that and get a cheap multiple, integer multiple speed up without having to build a more complicated distributed system and without having to think hard about like how you serialize data across things. I think there's just going to be a huge water lifting all the boats kind of benefit from that. So I expect we're going to see both of those. But already, I think the experience thus far has been pretty good in terms of being able to take important applications and parallelize them without an enormous amount of effort. I think the thing I'm most worried about the design is just like the general complexity budget of the language. In general, when you're designing a language, you should think about the power to weight ratio, right? Which is like, how much goodness do you get out of the design? How much things can you now do versus how much complexity and mess and do you get there? And like, I feel like this current set of work that we're doing is like, enormous untrammeled power and like a really large amount of weight. And like thinking about whether that balance is good is complicated. One of the things that we're trying to do there is to kind of have this kind of pay as you go kind of design where you don't have to swallow all the complexity at once. But I don't know, it's hard to be sure. If you go and read like the data race freedom paper, you'll be like, oh, that's kind of complicated. And like, you're not wrong. So we're thinking pretty hard both about how to land it in a way that's easy for people and how to teach people how to take advantage of this power. But I think that's for me the biggest question. I think I'm pretty confident the use cases will be there.
Management structure. Thanks, Ron, for the great presentation. Can you give us some insight into how teams were built to explore the migration? Like any learnings, any things you would change?
So you're saying this is about how in general, how teams at Jane Street are organized?
Or specifically this migration?
Oh, sorry. So the question, like the migration to do you mean like how was the work organized inside of the team that was responsible for fixing the problems? Or how do we roll it out to people?
How were decisions made? Like how did you benchmarks at stages? How did you progress project?
Got it. So the question is like, how did people kind of work through this process and make decisions? This is all done by what we call the OCaml language team. It's about 20 people all in. Part of what happens is, we have a few people who are like deep experts in kind of garbage collectors and runtimes, and they like thought really hard and did a bunch of careful experiments and looked at what was going on. We did a bunch of organization of this as a kind of sprint. We were aware that it was like really important to, in a focused way, get past this problem of the runtime not being ready. And so we tried to put off lots of other things and just soak as much time as possible into the process of getting this done. Again, like there's the 3-hour talk, which I'm also both we don't have time for and I'm probably not qualified to give, about all the kind of twists and turns about how things were discovered. But, I don't know, it's sort of the normal story of you look at examples, you do a lot of experiments, you break out perf, you break out all sorts of profiling tools. Actually, one great profiling tool I recommend to all of you is this thing called Magic Trace, which works great if you're on an Intel machine. Intel has built this awesome physical capability on their chips called Intel Processor Trace, which can capture at surprisingly low overhead every branch that your program takes and write it down in a ring buffer. And then we have a nice set of tooling that you can use on OCaml or C or C++ or Rust to grab that buffer and see down, with 10 nanosecond granularity, every single function call that happened and understand all the stack traces and stuff. And there's actually lots of performance problems can be solved by using sampling tools like perf, but sometimes just seeing 20 milliseconds of exactly what happened is the thing that you need. And so in general, having lots of good analysis tools and building analysis tools on the fly to try and understand things is a big part of how we just kind of worked through and figured out what needed to be done.
Thank you.
Cool.
How about let's set that as the last question?
Okay.
We wrap up.
So suppose that someone is thinking of building their own firm in the current day, and for whatever reason they don't want to use OCaml. Do you think it is a good idea to kind of think of some less popular language and kind of adopt that so that they have more control over how that language evolves and in terms of hiring and stuff like that?
It's a good question. I'd say the question is like, for someone who's thinking about starting a new thing now, like how would you think about picking a language? Does it make sense to pick some kind of, another comically obscure programming language where you have kind of more kind of control over it? It's complicated. I'll say in general, I feel like I personally and Jane Street in general have been lucky in many different ways, and lots of things have like panned out and worked out. And it's like hard to know why things were successful and why they worked out. So I like hesitate a little bit to tell you what you should do in starting your 23-person company. I do think, I guess I'd say, I think one thing that has been clear over the years is like building a language is hard. It's really hard. It takes a long time. It takes a lot of effort. If you're going to like invest a lot in a language ecosystem, you should make sure it's really giving you something kind of unique. And I think we got a number of things out of OCaml. Control is not a thing we got early. And I think unless you're doing something quite specialized, more specialized than what we're doing, I think probably controlling your own programming language is like not where you should start. And I think the control became more valuable. It's sort of like, the Facebook and PHP problem, like, congratulations, you've made like, billions of dollars on this like technology that's imperfect. Like now you're going to go fix it, right? And I think that's the kind of stage we're in now. Like any technology is imperfect. I would like to think OCaml is less imperfect than PHP, but we are nonetheless in a place where we are incented to fix it. I think actually the benefit that we got from using a kind of small niche language was less about control or evolution of a language, which, as I said, took really years, and more about attracting great people. As I said before, like, secretly, this is kind of about hiring, and finding great people is kind of the most important thing. And languages like OCaml are like not very popular. The set of people who know OCaml is like a set of measure zero, but it's not the empty set. And the people in that set of measure zero are pretty good. And so we got a lot of hiring advantages early on from using a language that, even though it was small, was like well loved by a group of very smart technologists. And I think that to me seems like a more kind of meaningful and durable benefit. And in fact, when we made this an early choice, there's an essay by Paul Graham called The Python Paradox, hilariously written at a time where Python was an unusual language. And it was about how companies that use unusual technology can attract great people as a result of it. And we actually read that at the time, and that was part of what kind of went into our thinking about the decision. And I think that kind of insight still is meaningful and holds true today.
Do you have any languages in mind in the current day which would fit into that kind of niche?
Not really. Yeah, I mean, I think there was a period where Rust kind of was like that, but I think Rust has become just kind of like larger and more mainstream. So I feel like it's less that kind of thing now. All right. Well, thank you all very much for coming.